Hi everyone. Okay, so in this session, I'm going to continue our lecture on topic 7, which is on the buckling of columns. Basically, in the previous class, we have discussed in detail on the definition of columns, and we have found that they have two classification of column, which is a slender and a short columns. In addition to that, we have using the marble analogy to describe the instability and buckling of columns. So in this session, we will focus on the Euler's formula. So without further ado, let's discuss in detail on this particular part. Okay, so basically the Euler's formula is given by this equation where the PCR is equal to pi square EI over LE square. Where the PCR is referred to the Euler's buckling load, Euler's critical buckling load, and the E is referred to Young model for the material. So basically the E for concrete is usually taken equal to 20 to 30 GPa. Meanwhile, for the steel, usually taken equal to 200 GPa. Okay, I is referred to the least second moment of area. LE is referred to the effective length of the column. Okay, so this equation has been derived based on the 5 assumptions that you can see here. So I don't want to discuss in detail on this. So I hope that you can read up by yourself and figure out how these 5 assumptions have been used to derive this particular Euler formula. What I wanted to highlight here is when you want to use this formula, you need to ensure that the least value of I must be chosen. Okay, so there is no issue when you deal with the circular and the square shape of a column. But if you deal with a rectangular column, so you need to choose the least value of I. So what you can see in these cross sections of a rectangular, they have a x-axis and a y-y axis. So you need to ensure that the I must be based on the least value from these both axes. Okay, so to discuss in detail for this particular issues, so we will use the ruler as our instant experiment. Okay, so you may grab your ruler and try to push that ruler. So you will find that the ruler will buckle about the y-y axis as what you can see in this diagram. Okay, so in the cross section of ruler is consists of the short side and the long side. So in this diagrams indicate that the short side is equal to B and the long side is denoted by the H. Okay, so you can see that here the ruler is buckled about the y-y. In other words, it's buckled along the short side. Okay, so we will check in detail. So we will prove that the ruler will buckle in the weak axis. Okay, so by considering that the B is equal to 2 mm and the H is equal to 30 mm and the L, the length of column is the length of ruler is equal to 150 mm. So you can see that the I-x-axis, okay, where we know that the I is equal to BH cubed over 12, and by substituting the value of B and H into this equation, you can see that the I-x-axis is equal to 4,500. Meanwhile, for in a y direction, you can see that the equations change to HB cubed over 12, and by substituting the value of B and H, you can see that the IYY is equal to 20 mm. So obviously you can see that the least value of I is referred to the YY axis. So this is the weak axis for the ruler. So no wonder this ruler has been buckled in about the YY axis. In other words, in the B direction. Okay, so by further assuming the value of LE is equal to 1.0 L based on the pin-ended conditions, and the value of E is equal to 0.0005 MPa. So you can see that the PCR in XX direction is equal to 22.21 newtons, and the PCR in YY direction is equal to 0.1 newton. So you can see that here the value of a PCR in YY is lesser than the value of PCR in XX. So we can conclude that the critical buckling load for this ruler is governed by the PCR in YY direction. Okay, so based on this slide, we can conclude that the axis which possess the least value of a second moment of area will govern the value of critical buckling load in a column. Okay, so I have proved that by using the simple experiment using the ruler. Okay, so I hope that you understand on this particular part. Okay, so let's move on the next slide. Okay, so besides the I value that influence the value of a critical buckling load, okay, so the LE, where is referred to the effective length, or sometimes we call it as a critical buckling length, also influence to the value of buckling load. Okay, so the LE is different based on different support condition. For instance, here you can see that for the pin-ended strut or the pin-ended column, so you can see that the LE is equal to 1.0 L. So L is referred to the total length of strut. Okay, meanwhile for the pin fixed conditions, so you can see that the LE is referred to 0.7 L. Okay, and for the fixed conditions, so the LE is equal to 0.5 L. And meanwhile for the for the cantilever column, once a point is a fixed, another one is a freely supported. So the LE is equal to 2.0 L. Okay, so I hope that you can identify how to figure out the different value of LE, the effective length, based on the different support condition in the column. Okay, so in this slide, we will identify and we will figure out the equation of slenderness ratio. Okay, so you know that the critical buckling stress, where the sigma CR is equal to critical buckling load divided by the area. So this is the common equation that you usually see in many situations where the stress can be obtained by force divided by area. Okay, but in this respect, we will talking about Euler's formula. Okay, so we have defined that for the PCR, the equation is given by the pi square EI over LE square. Okay, so and by substituting by the PCR with the detailed equation, so you can see found that the critical buckling stress is given by this equation. So we have the term A, and you know that the R square is equal to I over A. So where the R is referred to the least radius of gyration. Okay, so by okay, what you can see in this equation, actually you can factorize this equation, or you can rearrange this equation to become this equation, where you have seen that I over A has been factorized from the pi square E over LE square. Okay, so and we know that the I over A is referred to the R. Okay, so these equations will modify into this particular shape. Okay, so and we can rearrange this equation to get this particular form, where you can see that the equation become pi square E over LE over R square. So basically the term of the denominator term here is referred to the slenderness ratio. The LE over R is referred to the slenderness ratio, and we can denote this by the K. Okay, so LE over R can be denoted by the K value. Okay, so okay, so we have seen that the I, the second moment of area, and the effective length of column influence towards the PCR value. Okay, right here we will discuss in detail how the slenderness ratio will influence the critical buckling stress. Okay, so similarly for the rectangular cross sections, so the slenderness ratio can be in a x-axis and can be in a y-y direction. So that's why you can see here the slenderness ratio equation can be in terms of x-axis direction, where the Lx over Rxx, and in the y direction we have Kyy equal to Lyy over Ryy. Okay, so we will discuss in detail on how the slenderness ratio will influence the critical buckling stress in the next slide. Okay, so specifically in this slide. Okay, so and again, so we will use the ruler. So we will continue the experiment on the ruler. Okay, but here we will focus on the effect of slenderness ratio towards the critical buckling stress. Okay, so we have seen that this particular ruler will have been buckled about the y axis. Okay, so this is the dimension that we have defined previously. Okay, and the area of this particular ruler is equal to 60 mm square, and the E is remain the same. Okay, so by calculating the value of the RXX and the RYY, you can see that the RXX is equal to 8.66 mm and the RYY is equal to 0.58 mm. Okay, by assuming that the LXX and the LYY is equal to LE equal to 1.4 L, and this will give us the value will equal to 150 mm. Okay, so you can see that the value of KXX and the KYY is equal to 70.32 and 258.62 respectively. Okay, so by using this value of slenderness ratio, so you can further calculate the value of critical buckling stress. So in our x-axis directions, the buckling stress is equal to 1.65 times 10 to the power of negative 5. Meanwhile, in the y directions, you can see that the critical buckling stress is equal to 0.74 times 10 to the power of negative 5. Okay, so by comparing both of this value of a critical buckling stress in both directions, okay, you can see that the value of a critical buckling stress in the YY is lesser than the value of a critical buckling stress in the x-axis. Okay, so thus we can conclude that the critical buckling stress of the ruler is also governed by the YY axis. So in this slide, we can conclude that the axis which possesses the largest value of slenderness ratio will govern the value of critical buckling stress in a column. Okay, so I hope that you can figure out how the slenderness ratio will influence to the buckling stress equation. Okay, so I think that's it for the lecture. Okay, so we will continue on the examples.